Hey everyone, this is the first of what will probably be a couple of videos about Chapter 2, which covers the chemical composition of the human body. I know that many of you have had a full year chemistry class already. Probably a lot of this is going to be review from your bio and your chem classes, but I know that that's not necessarily true of everyone, and we'll take as much time as we need to get through the material so that everyone's feeling comfortable. I think it's important that we have a good grasp of the concepts in this chapter, because a lot of the physiology that we're going to be talking about will be going down to the molecular level to understand how things work inside the body. So the cover slide here has a protein. It's a human enzyme that chops up some of the cytoskeleton proteins that we have. Those are the sort of protein girders and structures that give our cells shape and help them to move. And this is one of the proteins that does the work of deconstructing cytoskeleton that's already been put up, and we have to do that on a pretty regular basis. And it's showing the difference in the configuration of the protein when it has been activated. And you can see on the left, the unactivated form looks a little bit different than the one on the right. Specifically, you can see in this area right here, in the activated form, the protein is collapsed on itself in that sort of waistline region there. And the red area that's very clear in the unactivated form kind of disappears when the protein is activated. And that happens with this protein when it binds to calcium ions, calcium 2+ ions will activate this protein. So when this protein needs to be active in the cell, the signal to switch it on is oftentimes going to be to release calcium ions in the cell. Okay, this is some really basic chemistry, probably going back to middle school for you guys, showing electron cloud and Bohr models of atoms. The electron cloud models are what we believe to be much more accurate representations, but the Bohr models tend to be simple and easy to interpret, so we still use those quite a bit. And they're not completely wrong. The real wrongness of a Bohr model would be showing electrons going around these very neat circular orbits, and that's just not the way it goes. We can never know the path of an electron. This is the quantum world of the atom, and things act a little weird. Remember, as we're going through the video here, to hit pause whenever you need to, so that you can take your time on some of the graphics that you see and some of the descriptions, and open up your book if you need to read something. And obviously you can use the web if you need to look something up too, but take advantage of the video format, hit pause whenever you need to. Over on the right, they're showing two hydrogen atoms that have bonded to form a single covalent bond. And in the Bohr models, they generally just show the pair of electrons kind of hooked up as if there's some sort of magic there. But if you know a little bit about physics, you know that electrons, which are both negatively charged, would tend to repel each other. And so it's not like the electrons are what the attraction is. The attraction in a covalent bond is the attraction of the positive nucleus of both atoms for the cloud of shared electrons that is between the two atoms. And that's the bond, that's the glue that holds those atoms together. We have these two positively charged nuclei. They have the protons, which carry the positive charges, and they're going to be mutually attracted to the electrons that are shared between the two atoms. And so they hold the molecule together by these shared mutual attractions. And they don't get too close to each other, because as soon as the two nuclei start to get too close to each other, the positives and positives and negatives of the electron clouds will repel each other and push back the other direction. This slide shows a little bit about isotopes using the example of the three most commonly occurring isotopes of carbon, the backbone element of all organic molecules. The most common type of carbon that exists out there in the wide world is carbon-12, and carbon-12 gets its name because in the nucleus there are 6 protons and 6 neutrons. That 12 number in the name carbon-12 is the mass number, and the mass number is equal to the number of protons and the number of neutrons in an atom. So the protons and the neutrons are the particles that have the greatest mass by far in an atom. Electrons are very, very lightweight compared to either a proton or a neutron. So most of the mass of an atom is the mass of the protons plus neutrons. Carbon-13 has 7 neutrons, and so the mass number again, protons plus neutrons. And then the radioactive form of carbon, carbon-14, has 8 neutrons. They all have 6 protons because it ain't carbon if it ain't got 6 protons. Carbon is number 6 on the periodic table. That means it has 6 protons. That is what defines carbon. And the neutrons that are different between these 3 isotopes will add weight, mass, to the atoms, but they really don't affect it much otherwise in terms of how that carbon atom will behave when it's interacting with other atoms in our bodies. This slide just shows 3 different ways that we represent molecules. The structural formula is the one that is highlighted in the shaded area for both of these molecules. There's methane, which is natural gas on the left, and ammonia, which is a byproduct of protein metabolism. We are making it inadvertently, but making it all the time as we break down proteins. The bigger diagrams in here show sort of Bohr representations with the bonding, the covalent bonding, as it was demonstrated in the previous slide. And then the third representation on the slide here is what we call space-filling models. And the space-filling models of molecules are showing the volumes that are occupied by the electron clouds of the individual atoms. So it gives us rough sort of geographic representation of the whole molecule. And I think I should have said geometric there. It's just geometry, not geography. All right, you have probably heard that water is a wacky molecule, and if you haven't heard that, let me tell you, water is whack. Water is one of the weirdest substances in the universe. It behaves very strangely for a small molecule, and we'll talk about some of these ideas in detail. Water molecules are 3 small, simple atoms, an oxygen covalently bonded with single covalent bonds to 2 hydrogens. But because of the orientation of the hydrogen atoms on the water molecule as a whole, and because of the fact that oxygen has a very strong attraction for electrons, the shared electrons that are in this covalent bond and in that covalent bond, those electrons aren't being shared equally. The oxygen atom pulls those electrons much more strongly than the hydrogen atoms, and so those shared electrons wind up spending a lot more time on this side of the molecule than they do on the other. And so we say that water is polar. So if something is polar, it just means it has opposite sides, like the 2 poles of a magnet, north and south. Electrical poles would mean positive and negative, and water molecules are very polar because of this uneven distribution of electrons caused by oxygen's ability to pull the shared electrons on one side. And so when we write the structure for a water molecule and we try to represent the kind of positive and kind of negative aspects of the molecule, we use these lowercase Greek letter deltas to represent partial charges. So it's not an ion, it's not a full ionic positive or negative charge, but that hydrogen side of the molecule is distinctly positive and the oxygen side is distinctly negative. Below is a representation of a really important reaction that happens whenever you have water. Water molecules cannot leave each other alone, and when left to their own devices, they will react. Two water molecules will react with one another. One water molecule will steal a proton, that is a hydrogen atom without its electron, and so the products are what is called a hydronium ion, H3O+, and a hydroxide ion, OH-. And now we've got real charged particles, and this is the reaction that is of big time importance when we're talking about pH and the acidity of cells. You guys have probably all seen this before, perhaps multiple times. This is showing the formation of an ionic bond. And ionic bonds are simple electrical attractions between positively charged and negatively charged ions. And this shows, the way it almost always shows in a textbook, it shows an electron. Well, I wanted to show an electron. There it goes. Shows an electron being transferred from the sodium atom over to the chlorine atom. And now we have a sodium ion, a positively charged sodium ion, that has a very stable configuration of electrons with the maximum of 8 electrons in the outer shell of the atomic structure. The maximum number that can exist in that second energy level is 8, and that's a stable configuration. And so when a sodium atom loses that one electron, it becomes more stable. In fact, we really don't find sodium atoms in nature. They never hold on to that lone third level electron. They always dump it off on someone. And chlorine atoms almost always in nature exist as chloride ions for the same reason. When they pick up that 8th electron in their third energy level, that's when both atoms are following what we call the octet rules. The octet rule basically states that when atoms have a full octet of electrons in their outer energy level, when they have 8 electrons in their outer energy level, they tend to be very stable. And so they stay that way if they're stable. If they don't have an electron, a full complement of electrons in their outer energy level, then they're not very stable and they tend to react until they get into a more stable configuration. And so we have a positive ion and a negative ion, and positives and negatives attract, and that is the ionic bond. This kind of representation is what you always see, as if there are a bunch of sodium atoms and chlorine atoms out there in nature just waiting to bump into each other. But that's just really not true. Most of the sodium in the universe is a sodium ion already. Those atoms would have lost that electron not long after the sodium was formed. Here we're going to show something really important about why water is as weird. One of the reasons why water is as weird as it is. Water is sometimes called the universal solvent. That means virtually everything dissolves in water. And this is showing a bit about why that is so. We have a crystal of ionic solid up here, and this could be sodium chloride, like we just saw forming in the previous slide. So we have positive and negative ions all stuck together in a small crystal of, let's call it sodium chloride. And sodium chloride dissolves very easily and quickly in water because the water molecules have those, remember, those positive and negative sides to them. And the negative ions that are on the surface of the crystal of ionic solid would attract the hydrogen sides of all of those water molecules that are bumping into them. And as those water molecules interact with that negative ion, they will pull it away from the crystal, and ultimately those water molecules will surround the negative ion with all the hydrogen ends of the molecules pointing in towards the negative charge. The same thing is happening with the positively charged ions. They're being pulled away from the crystal by the negative parts of the water molecules, the oxygen sides of the molecules. And those kind of negative oxygen atoms in the water molecules will attract to those positive ions, and when enough of them are interacting with it, they can pull it right away from that crystal of sodium chloride. And ion by ion, those crystals will dissolve into solution, and once the water molecules get them all surrounded, it's difficult for those positive and negative charges to get at each other and attract each other again. So once it's dissolved, the substance tends to stay dissolved in the water. All right, this will be the last slide for this video, I think. We are going to talk about a hugely important thing in biochemistry, and that is the hydrogen bond. Hydrogen bonds are a relatively weak but really important attraction between molecules. And hydrogen bonds form whenever we have hydrogen atoms, like this one, bonded to another atom that has a much stronger attraction for electrons. And we call the measure of that attraction for electrons electronegativity. And when an atom has an especially strong attraction for shared electrons, like the oxygen atom does in the water molecule, we would say that it's very or highly electronegative. And so in this bond between the hydrogen atom and the oxygen atom in this water molecule, the electrons are not being shared equally. The electrons are being pulled down towards that oxygen. And so the hydrogen, remember, winds up being kind of positive. And when that kind of positive hydrogen atom on one molecule interacts with a kind of negative oxygen atom, or it also could be a nitrogen atom, on another molecule, that attraction is relatively strong as attractions between molecules go. And so in a sample of liquid water where the molecules are able to move around and orient themselves the way they might, they tend to move around so that the hydrogen atoms of one molecule orient themselves towards the oxygen atoms of another water molecule. And that weak attraction between the hydrogen atom of one molecule and the oxygen atom of another molecule is called the hydrogen bond. And that hydrogen bonding is really important, and it gives water some of its weird behaviors, but it's also, we're going to find out, really, really important for the structure of DNA, for the interactions between DNA and RNA, and for the structures of proteins. And that is what makes the living world go round. On the PowerPoint presentation that I put into the Google Classroom file for you for this assignment, you can click on the PowerPoint presentation, open it up, and watch the video that I linked onto the PowerPoint presentation. I'm doing this on my iPad, so it's not going to work on this one. I hope it didn't bore you too much. We'll see you in class soon.